Have you ever stopped to think about how some of the biggest problems on our planet actually come down to some of the smallest things like molecules? Well, today, we're going to do just that. We're going to explore the heartbreaking crisis facing our coral reefs to understand the basic chemistry of solutions. You'll see how the same science that makes salt disappear in your soup is literally reshaping our world. Okay, let's get into it.
All right, first up, we've got to grasp the scale of what we're talking about here. This isn't just a small local issue. No, this is a global crisis that's all happening in the very water that makes up most of our planet.
I mean, just let that sink in for a second. These incredible, vibrant underwater cities, they support a quarter of all known life in the sea. That means 1 out of every 4 creatures you can imagine in the ocean depends on these reefs to survive. The stakes couldn't be higher.
That number, 25%, it's just staggering. It represents this unbelievable concentration of life in one type of ecosystem. It's not just a pretty place, it's a vital, bustling metropolis for the entire ocean.
And the crazy part is, the biggest threat isn't always something obvious like a giant oil spill. Nope, it's something invisible. A quiet but radical change happening to the chemical recipe of the ocean itself. And that right there is the big question we're tackling. How can some basic chemistry principles shed light on this massive environmental problem? Well, the answer starts with seeing the ocean for what it really is, a giant, complex solution. So to really get to the bottom of this, we need to zoom all the way in. We've got to go back to Chemistry 101 and break down what a solution actually is on a molecular level.
So, simply put, a solution is just a super even mix. It's where different things are blended together so perfectly that you can't see the individual parts anymore. And seawater, it's pretty much the most famous and important solution on Earth.
Now, in every solution, you've got a main player, the substance that does all the dissolving. We call that the solvent. And in the ocean, and for most life as we know it, that all-star solvent is, you guessed it, water.
Everything else that gets dissolved in that water is called a solute. For our story, the really important solutes aren't just the salts that make the ocean salty. It's also the dissolved gases, like the oxygen that fish need to breathe, and the one that's causing all the trouble, carbon dioxide.
So how does this magic act of dissolving actually work? Well, check this out. Water molecules are polar, meaning they act like tiny little magnets. When you drop salt in, these water magnets swarm the salt ions, grab onto them, and literally pull them apart in this molecular tug-of-war. They then get scattered perfectly evenly, and poof, the salt seems to vanish.
But, this whole dissolving thing isn't a free-for-all. It's not chaos. Turns out there are some very specific rules that control just how much stuff you can dissolve into something else. And that limit has a name, solubility. A good way to think about it is like a sponge. A sponge can only soak up so much water, right? At some point, it's completely full. Well, it's the same idea with the solvent. It has a maximum capacity for any given solute. This whole idea of a limit leads to 3 different states. You can have an unsaturated solution, which means there's still room for more stuff to dissolve. Then there's saturated, which is totally full at its limit. And then you get this really weird state called supersaturated, where you've tricked it into holding more than it should. It's super unstable, one little shake, and all the extra stuff can just crash right out. Okay, but here's where it gets really interesting and super important for our oceans. Temperature completely changes the rules. For most solids, like dissolving sugar in your coffee, hotter is better. Higher temperature means you can dissolve more. But for gases, it's the complete opposite. The warmer the water gets, the less gas it can hold.
And that brings us right back to the crisis. As our planet gets warmer, the oceans warm up too. And because of that simple rule of chemistry, the water just can't hold on to as much dissolved oxygen. This creates huge dead zones where marine life literally can't breathe. It's a direct, chemical consequence of a warming planet.
But temperature isn't the only thing at play. There's also pressure. This is explained by something called Henry's law, which sounds complicated, but it's not. All it says is the more pressure from a gas you have pushing down on a liquid, the more of that gas will dissolve into it. Just think of a can of soda. It's packed under high pressure to force all that fizzy CO2 to stay in the liquid.
And here is the other shoe dropping for our coral reefs. As we pump more and more CO2 into the atmosphere, we're increasing the pressure of that gas on the ocean surface. So, just like that soda can, more CO2 dissolves into the water. This forms carbonic acid, making the ocean more acidic, and that acid starts to dissolve the very calcium carbonate skeletons that corals need to build their homes.
So we've seen how solutes can change the chemistry of water, but they also give it some other really cool abilities, almost like superpowers. Let's take a quick look at these.
These powers are known as colligative properties, and the most important thing to remember here is that it's all about the number of solute particles, not what they are. It doesn't matter if it's salt or sugar or something else entirely. It's about quantity, not quality.
You've definitely seen this one in action. It's called freezing point depression. When you add solute particles to water, they basically get in the way, making it harder for the water molecules to line up and form ice. So, the water has to get even colder to freeze. That is exactly why we pour salt on icy roads. It lowers the freezing point and melts the ice.
And believe it or not, the exact opposite is also true. Those same little particles make it harder for water molecules to escape as steam. This means you have to pump in more heat, raising the temperature to get the water to boil. We call that boiling point elevation.
So we've gone through all this chemistry. What's the big takeaway? We started this journey looking at coral reefs, but what we've learned is so much bigger than that.
The simple truth is that the health of our oceans, the way our own bodies work, the very air we breathe, it is all governed by the delicate balance of solutions. These aren't just concepts in a textbook. They are the fundamental operating instructions for life itself.
When you step back and look at it, our entire world, from the atmosphere to the oceans to the blood flowing in our veins, is just a series of incredibly complex and fine-tuned solutions. And that leaves us with a really big and honestly a pretty unsettling question. By changing the concentration of things like CO2, are we changing the very formula for life on this planet faster than it can possibly adapt?